So hey everyone, I'm Isaac and I am a graduate student and a researcher from Northeastern University. And today we'll be discussing a lot on world models. So world models has been at this cornerstone of the recent advancements in large language models and vision-based transformers. So apparently a professor named Jan LeCun. Uh, he is a distinguished researcher and he has proposed this new architecture called JEPA, and they have come up with iJEPA, vJEPA models, which can help reconstruct images, generate videos, similar to how LLMs work in Gemini and several Llama models that produce videos based on given inputs. So we will be quickly reviewing a 1 hour lecture given by Jan LeCun on world models. I will try to make it concise as possible based on my understanding so that you guys can easily understand for those who don't have much of a background or knowledge in LLMs. To begin with, here are some of the slides that I was able to find in one of the LinkedIn posts presented by one of my fellow connections from NYU, and here it says that shaping the future of artificial intelligence. So what Jan LeCun strongly states is that the current traditional way of predicting new tokens based on a given uh, set of tokens fed to an LLM is not going to get us to the level of artificial general intelligence. And for the audience who don't know what AGI is, AGI is basically mimicking the level of intelligence that a human possesses, and it's not like a typical average human. It's more of a person who has like actually pursued a PhD and has like a high level of IQ and knows a lot of information or facts. So to begin with, we will talk about the some disadvantages that LLMs have. So he has touched upon resources, computation, and the time taken to train LLM models, and how the new architecture that he has proposed can reduce all the time, and what kind of comparison that he gave uh, regarding the new architecture. So to begin with, he compares three different basic types of learning, which is supervised learning, reinforcement learning, and self-supervised learning. So supervised learning, as we all know, uh, it's a, is a way of learning by giving a set of examples. So let's say I want to find out whether an animal that's crossing by me is a cat or a dog. I will have to know it based on a certain set of flashcards or something that I had learned previously, or by some example, uh, let's say in YouTube video or something. But reinforcement learning is basically trial and error, and uh, which is something that people think that humans learn by that way, but humans actually learn through the method of self-supervised learning, which is more of correcting themselves every time when they see something new, and they make sure that they update themselves based on a given set of inputs which is presented to them every time. So the thing is, he compares human brains to LLM models, and simply says uh, the way that humans learn things very easily and very quickly is typically not the way that LLMs are learning right now. So LLMs are taking um, a lot of time and a lot of data to be trained. So I think you guys have heard of like the large scale construction of large data centers being spent like billions of dollars in various cities like Texas and so on. And he says that the amount of data uh, that is typically trained for an LLM is about 10 to the power 14, which is it's a lot of data, and it takes a typical human to for 1.5 million years to understand and learn that data, which is practically not possible. So in order for him to compare that with a 4-year old child, he tells that a 4-year old child typically takes only 30 minutes of YouTube video content uh, to understand such a um, uh, complex information or any kind of such similar type of data of that size. So what he begins with is he tells us about autoregressive LLMs. So as I told, it takes in typical LLMs it takes the previous set of words and then predicts uh, the next set of tokens, which is again fed to the LLM to move on and predict the outcome or whatever the desired task is. So what happens here is there's a lot of uncertainty in the outcome as well. Um, you there's a lot of chance that it might go wrong and it might produce the wrong results. Uh, and if there is a change in a set of sequences or symbols or tokens uh, in the middle of the process, there is a high likely that the entire process will go down and um, the outcome will be typically wrong. So generative models work is that they have a structure of an encoder and a decoder. For those who don't know about GANs, I will cover about GANs if you guys request on it. But if you guys don't know about GANs, I think you should look it up somewhere in YouTube. You will find a tutorial. But more of it will uh, be given upon your request. So this is how typical autoregressive LLMs work, and I think we have covered that in the previous slide. And so what he's telling here, the pie chart that he's given here is the set of all possible predictions or outcomes, and the red part is the correct set of predictions. So an LLM has different types of outcomes or possibilities, and the probability given that you get the correct set of answers for any given task is measured by 1 minus e to the power n. So this diverges exponentially and it's not fixable uh, because of the current architecture in LLMs. It tells that generative models suck and LLMs are doomed. So what's next? He wants to build a model uh, that has a representation that brings representation of a certain output, and it has to be optimized until we reach the actual answer that we want. To put it in this simple words, it's more about uh, optimizing till you get the correct answer, and then the optimization part we will be using something called as an energy function, which is a similar function to how physicists calculate uh, certain predictions or errors. and here he states that it's a scalar output function, and if it would be close to 0 if the prediction is correct, and it would rise if the predictions are wrong. So here's a task of moving from his university campus to the Paris, and the consideration of different things like going down the street, grabbing a taxi to airport, train or taxi, distance to airport, which airline, and so on. And so he tells that a world model would typically consider a lot of these things. And moving on, he talks about, this is the brain and the different parts of the brain that mimics the task of a world model. And you can see perception actor, world model, uh, critic cost or intrinsic cost, which is basically the type of cost functions that we use like to predict the errors. And we have to represent the world as an output as well, and making sure that it matches the given input. So uh, another here is a more detailed explanation of world models. So given that we have an input, set of images or videos, we first have like an initial state called which is s of x, and then we pass it to an encoder, and with an action, and we predict a set of states um, for a given um, outcome. And then we have to find the difference between the actual and the predicted state, so which is where we have like an energy or a cost function. Such an energy function can be turned into a probabilistic function using a Gibbs distribution, uh, which I think you guys are aware of. And then once the error is calculated, we make sure the energy is maximized, or the cost function is maximized, so that the current representation of the state is used to determine the outcome. So it's very uh, useful in determining the correct state. So here are some examples that he had covered to predicting the next frame of the girl celebrating the birthday. He has different cars in lanes, and then predicting the car in the lane that was uh, not fed to the LLM, and then the model, and then predicting the position of the car. But there's a lot of uncertainties and errors in the prediction. The latent representation, we should make sure that the input data can be used uh, to to um, to map the energy function, because the energy function helpful to withhold the entire set of samples or data available on the in-depth architecture of world models, and how you can train these models to test them out. There are few people who implemented the JEPA architecture using certain resources. To begin with, here are some papers on self-supervised learning from images with the joint embedding predictive architectures, and they literally proved that iJEPA is quite better than the MAE models and data to vec models or ibot models. And in vJEPA or video JEPA models, they have proved that the input videos were quite similar to what the vJEPA model had predicted. So these are quite interesting insights that were produced from Meta. There's a lot of other researchers from DeepMind and so on, several research institutes working on several new models. I will be covering some interesting models, interesting insights that we're getting on our path towards AGI. And here is vJEPA 2, is self-supervised video models enabling understanding, prediction, and planning. And this, I think, came out very recently from Meta. And yeah, so this is a foundational self-supervised foundation model, pretty much understanding, predicting, and planning different tasks, like for example taking a bottle, and this one is forward 1.5 somersault, no twist, ankle, and so on. So this is the level of realism we are getting with the world models or JEPA architectures and how they represent states and using energy functions to map them. So to cover more about such advancements, we will, yeah, so I think this is pretty much clear. And to cover more about such advancements of different models that is being produced, I'll just let me know in the comments. I'll make sure to make some time and catch up on such information from like groundbreaking information from different institutes here. And that is all from me for today. I look forward to seeing you all in the next video, and subscribe for more videos.